Thank you for giving me this opportunity of making this presentation. And I'm from DENSO, and we are collaborating with Tohoku University. In this talk, I propose iterative optimization method for solving the ground state search of the POTS models using the deep quantum annealer. Here is the agenda of this talk. First, I talk about the motivation of this study. And next, I briefly explain one-hot encoding, which is typically used to solve integer optimization problems using the deep quantum annealer. And thirdly, I show a first-order phase transition occurs during quantum annealing of the ferromagnetic POTS model, indicating quantum annealing cannot solve the ground state search of the ferromagnetic POTS model. After that, I propose iterative optimization method for the ferromagnetic POTS model to avoid the first-order phase transition. Then, the applicability of the proposed method to the POTS class model is discussed. And lastly, I summarize this talk. The deep quantum annealer implements quantum annealing and is expected to efficiently solve combinatorial optimization problems. The quantum annealer can solve quadratic unconstrained binary optimization problem or the ground state search of an Ising model. Inputs to the annealer is Q matrix or J matrix and H vector, and it outputs candidates of optimal solutions. However, cost functions of many practical problems are defined by integer variables. The general form of the integer optimization problem is shown here, where Si is the integer variable. Examples of integer optimization problems are shown here. In the graph coloring problem, a graph with n vertices and a set of q colors are given, and it is required to color each vertex without edges connecting vertices of the same color. In the job assignment problem, n jobs and q computers are given, and it is required to assign each job to one of the computers, such that the total computational time is minimized. Furthermore, the cost functions of the graph partitioning problem and the traveling salesman problem are defined by integer variables. So we need efficient optimization methods to solve integer optimization problems by the deep quantum annealer. In this study, I focus on this simplified integer optimization problem as a first step, which is one of the most basic forms of the POTS model, and we propose iterative optimization method for solving it using the deep quantum annealer. Next, I briefly explain one-hot encoding, which is typically used to solve integer optimization problems using the deep quantum annealer. In this study, I focus on the ground state search of the POTS model as shown here, where Si represents integer variable with Q components, and delta denotes the Kronecker delta. Jij contributes to the cost function only when Si is equal to Sj. This optimization problem can be represented as the binary optimization problem under constraints using the one-hot encoding, as shown below. Xqi is the binary variable, which is assigned to the component Q of Si, and it is equal to 1 only when Si is equal to Q. Jij contributes to the cost function only when both Xqi and Xqj is equal to 1. This figure shows the problem graph of the cost function, where vertices and edges represent the binary variables and the interactions between them. Q binary variables are assigned to each integer variable, and the one-hot constraint is imposed to select exactly one component for each integer variable. The binary optimization problem can be represented as the Ising form using this transformation. The second term is a constant because the sum of sigma qi with respect to small q is constrained to a constant, and the third term does not depend on the Ising spins. Therefore, the cost function to be minimized is the first term, which is the sum of the Hamiltonians of q-independent Ising models, whose interactions are given by Jij. In order to solve optimization problems using the Diev-Quantum manila, the unconstrained cost function is required, and it is achieved by introducing a penalty term. The second term is the penalty term, which is minimized only when the one-hot constraint is satisfied, and the parameter lambda controls the strength of the penalty term. Then, by expanding the penalty term, we obtain the optimization problem as shown below. The first term is the sum of the Hamiltonians of q-independent Ising models, and the penalty term consists of the fully connected antiferromagnetic interaction and the longitudinal magnetic field. Next, I show a first-order phase transition occurs during quantum annealing of the ferromagnetic Potts model, indicating quantum annealing cannot solve the ground state search of the ferromagnetic Potts model. This is the cost function of the fully connected ferromagnetic Potts model. The first term is the sum of the Hamiltonians of q-independent ferromagnetic Ising models, and the penalty term consists of the antiferromagnetic interaction and the longitudinal magnetic field. Hamiltonian of quantum annealing is shown below, where transverse magnetic field is applied to induce quantum fluctuations, and gamma controls the strength of the transverse magnetic field. We investigate the phase transition order during quantum annealing of the ferromagnetic Potts model. The phase transition order is strongly related to the computational time of quantum annealing, and if the first-order phase transition occurs during quantum annealing, the computational time typically increases exponentially with the system size. This is the partition function of the ferromagnetic Potts model, and we can apply the mean field theory to the first term, which is the sum of the Hamiltonians of ferromagnetic Ising models. By introducing ferromagnetic order parameters to each ferromagnetic Ising model, we obtain the free energy as shown below, where epsilon is the lowest eigenvalue of the effective Hamiltonian. We can numerically calculate the lowest eigenvalue of the effective Hamiltonian for small q, and the ferromagnetic order parameters are determined as the minimizer of the free energy. Then, I reduce the number of ferromagnetic order parameters using the symmetry of the system induced by the one-hot constraint. This figure shows one of the ground states of the ferromagnetic Potts model, where all integer variables are aligned to the component 1. This configuration consists of the ground states of the ferromagnetic Ising model, and one ferromagnetic order parameter is equal to -1, and other ferromagnetic order parameters are equal to +1. Because the one-hot constraint divides the ferromagnetic order parameters into two groups, we assume that one order parameter is equal to n-, and q-1 order parameters are equal to n+ at any gamma. And then we search n+- that minimize the free energy. These graphs show the ferromagnetic order parameters n+- as functions of gamma for q equals 3 and q equals 4. For both cases, n+- are positively biased at a large gamma, and they discontinuously change to the positive n+ and the negative n-, indicating the first-order phase transition. These results imply quantum annealing cannot search the ground states of the ferromagnetic Potts model efficiently. The first order phase transition is caused by the positively biased n plus minus at a large gamma, which originates from the longitudinal magnetic field of the penalty term. Next, I propose iterative optimization method for the ferromagnetic Potts model to avoid the first order phase transition. In the first iteration, this optimization problem is solved, where the one-hot constraint is replaced to the half-hot constraint. And Q/2 components are extracted in the first iteration. The unconstrained cost function is shown here, and the second term is the penalty term of the half-hot constraint. The penalty term consists of only the antiferromagnetic interaction and does not contain the longitudinal magnetic field. Therefore, the first order phase transition is expected to be avoided in the first iteration. This figure shows one of the ground states in the first iteration, where the component 1 and 3 is commonly selected for each integer variable. The half-hot constraint is satisfied, and this configuration consists of the ground states of the ferromagnetic Ising model. This configuration obviously minimizes the cost function because the cost function is the sum of the Hamiltonians of Q-independent ferromagnetic Ising models. Then, in the second iteration, the Ising spins assigned to the component 2 and 4 are fixed to +1, and the optimization problem with the Ising spins assigned to the component 1 and 3 is extracted. The half-hot constraint is imposed again, and this optimization problem is equivalent to the ground state search of the ferromagnetic Potts model with Q/2 components. Therefore, the first order phase transition is expected to be avoided in the second iteration as well. By solving the optimization problem in the second iteration, we obtain the ground states of the ferromagnetic Potts model as shown here. Thus, if the optimization problem in each iteration is successfully solved, we can retrieve the ground states of the ferromagnetic Potts model without undergoing the first order phase transition by the proposed method. We can verify that the first order phase transition can be avoided under the half-hot constraint. This is the unconstrained cost function, and we can apply the mean field theory to the first term. By introducing the ferromagnetic order parameters to each ferromagnetic Ising model, we obtain the free energy as shown here, where epsilon is the lowest eigenvalue of the effective Hamiltonian. Then, as is the case under the one-hot constraint, we reduce the number of ferromagnetic order parameters using the symmetry of the system induced by the half-hot constraint. In this case, we assume Q/2 order parameters are equal to m-, and the rest of the ferromagnetic order parameters are equal to m+. Then, we search m+- that minimize the free energy. These graphs show the ferromagnetic order parameters m+- as functions of gamma for Q = 4 under the half-hot constraint under the one-hot constraint. M+- are not biased at a large gamma under the half-hot constraint, and they continuously change to the positive m+ and the negative m-, indicating the second order phase transition. Thus, the first order phase transition is avoided under the half-hot constraint, and the computational time of each iteration is expected to be polynomial. Furthermore, we can verify that the first-order phase transition can be avoided even in infinite limit of Q. This is the unconstrained cost function, and we can apply, in this case, we can apply the mean field theory to the second term as well. By introducing ferromagnetic order parameters, large M, to each half-hot constraint, we obtain the free energy as shown here. Then, by assuming large M does not depend on I, it is easily shown that large M is equal to 0. Consequently, we obtain the saddle point equation for M plus minus as shown here, which is identical to that of the ferromagnetic Ising model. This result indicates the first-order phase transition can be avoided even in infinite limit of Q. Next, I discuss the applicability of the proposed method to the Potts-Glass model. First, I show saddle point equations under the half-hot constraint. Saddle point equations of the Potts-Glass model under the half-hot constraint are identical to those of the SK model in infinite limit of Q. This is the cost function of the Potts-Glass model under the half-hot constraint. The first term is the sum of the Hamiltonians of Q-independent SK models, where probability distribution of Jij is given by Gaussian. Under the assumption of the static approximation and replica symmetric solution, we obtain saddle point equations as shown here, that are identical to those of the SK model. This result indicates simulated annealing and quantum annealing of the Potts-Glass model under the half-hot constraint undergo the same phase transition as the SK model in the first iteration. However, it is unclear whether we can retrieve the ground state of the Potts-Glass model by the proposed method. This figure shows one of the ground states in the first iteration. And this configuration consists of the ground states of the SK model. Here, GS and GS bar denote the ground states of the SK model, and the Ising spins in GS bar are all reversed from GS. In order to satisfy the half-hot constraint, GS and GS bar are paired in this configuration, and as is not the case for the ferromagnetic Potts model, different components can be extracted for each integer variable, as shown here. Therefore, the problem graph in the second iteration is different from that in the first iteration. And the cost function in the second iteration is the sum of the SK model with bond dilution. It is very difficult to analytically show the validity of the proposed method to the Potts-Glass model, and it remains as a future work. So this is the summary of this talk. Quantum annealing of the ferromagnetic Potts model undergoes the first-order phase transition, indicating quantum annealing cannot solve the ground state search of the ferromagnetic Potts model efficiently. The first-order phase transition under the one-hot constraint is caused by the longitudinal magnetic field of the penalty term. We propose the iterative optimization method under the half-hot constraint to avoid the first-order phase transition in the ferromagnetic Potts model. And it is unclear whether the ground states of the Potts-Glass model are obtained by the proposed method. It is future work to investigate the validity of the proposed method for various integer optimization problems. Thank you.
Some questions?
Thank you for the interesting talk. I do think that you can avoid the first order phase transition, but I guess this type of model has been studied before for Q equals 2, and it was shown that it's not the gap at the quantum phase transition that determines the runtime of the quantum adiabatic algorithm, but there are many, many other gaps, smaller gaps, first order gaps, after that basically determine the runtime. And so even if you do take care of at the gap at the phase transition, it turns out that it's still an exponentially hard problem to solve because of many, many other gaps that come inside basically the spingless phase. And I can give you a reference if you wish, but that's basically the current understanding.
So the ground state search of the post-class model cannot be solved by the proposed method. So essentially difficult problems cannot be solved by any methods, I think. So, but the proposed method but it is very important to extend the class of problems which can be solved by quantum annealing, and at least the proposed method can solve the ferromagnetic post model. This is an important thing.
Okay, thank you.
So if you look at not the Potts model version of this, but the Ising model version of this, then work by Nishimori-san and collaborators, it's been shown that by modifying the adiabatic path, or by reverse annealing, or other methods which do not involve iteration, and therefore do not require additional computation time, the first order phase transition can be avoided and be turned into a second order phase transition.
So, sorry, I couldn't hear your question. So,
please talk to Nishimori-san.